Well, thank you. And it's nice to join you from Calgary, Alberta. The temperature was 85 degrees today, so not as hot as some of you guys are enjoying or not enjoying. So I was asked to give a reprise of a presentation I've done previously on modern diversity reception. And I'm going to take you through a slide deck, explain all it is. I've only got mathematics in one slide. No, not 85 Celsius. I was converting to real degrees, 85 Fahrenheit. We were about 29, 30 Celsius. But one time when I gave this presentation, halfway through it, I showed a video. And one of the participants afterwards said, you know, you should just start with the video because it really says it all. So I'm going to do that. And I have to share my screen, which means I have to fiddle around with this stuff. So we'll start out.
You need to share that up. Be sure to put the click that you put on the lower left side of the place for sharing videos and such.
Yeah, so you should be seeing my video right now.
No, not yet. Oh, Dennis was saying this ain't okay, so I got you another screen. There you are.
Okay, so the video is not running. I'm going to tell you what you're going to see, and then we'll watch it. So hang on a sec. It says I'm supposed to join a meeting. Am I still on here?
Yes, you are.
Okay, so a few years ago, I started getting a lot of interference from a neighbor, and I tried to figure out how to get rid of that RFI. And so what I did was I went through a whole bunch of stuff I'm going to tell you about, but here's where I ended up. And I want you to see how well diversity reception can get rid of RFI from a neighbor.
Starting the economic development and improving people's lives as it faces.
Okay, when you see the noise, okay, I've got two antennas here on two different receivers coming through on one screen. And when I mix the two receivers together, I can get rid of the noise. Right now, I'm just on receiver 1, then I'll show receiver 2, and then I'll show the combination. And I can vary the phase between the two receivers and also the amplitude with this control over here.
What Kim called a great life and death struggle. Plenary meeting of the 8th Central Committee of the Workers' Party of Korea, which began on Monday. You can find at our website, voanews.com. We also have a mobile app that you can download via remote. I'm Marissa Milton, VOA News.
Okay, so you could see in that video that I was getting rid of about 40 dB of interference from my neighbor's halogen lights in the kitchen, and that's how well it works. So now I want to go back and say, okay, how did I get to this point? And let's see if we can make this work. Okay, so modern diversity reception. I'm going to give you a bit of history. I'm going to tell you how it works. I've already shown the demonstration video, which you can edit back in, and I'll tell you what I do at my end. So what is a modern diversity receiver? Are you getting slide number 3?
Yes.
Okay. A modern diversity receiver has 3 characteristics. It's a dual channel receiver. And that means it's 2 receivers, usually in one box, that you can run a separate antenna on each receiver, and you space the antennas apart for diversity, space diversity. The second characteristic is the channels have to be coherent. You need a common local oscillator or DDC clock and a common ADC clock, and you need to generate synchronous baseband data from each of the receivers. And thirdly, you need to be able to combine the channels at baseband and vary the amplitude and phase to combine signals And you can combine the signals from these two receivers constructively or destructively. But everything's got to be synchronized together. They've got to be coherent, which means lockstep with each other, but you can play around and you can vary the way you combine the signals together. So right now, state of the art, this is still true, I think, for in 2022, there's 5 leading ham transceivers have dual channel coherent signal chains. And they're available from Elecraft, from Yaesu, from ICOM, from Flex, and from Anan. But only 2 of these provide synchronous IQ data output, and that's from the Flex and the Anan. But only one of them lets you combine the data at baseband for modern diversity reception, which is what I showed you earlier, and that's the Anan. So it's really, in my view, it's sad, because most of the receivers coming out today, the transceivers, actually have these coherent dual channel receivers. But to get diversity reception, they expect you to put on a pair of headphones and figure it all out in your head, as opposed to letting you adjust the phase and amplitude digitally to make the magic work. There's 3 features of modern diversity reception, and I'm going to tell you what each of them is. The first is diversity gain, which is the original value proposition from 1926, which is how they used multiple receivers to improve shortwave around the world. Array gain, which is the basic concept of taking 2 or more antennas and phasing them against each other. And the third is noise cancellation, which is really the most modern and most recent value proposition that I'm trying to push. These are the use cases. Beveridge invented the diversity gain to fight multipath fading in 1926. We've been doing beam forming or array gain since 1905 and doing it digitally since the 1960s. And the local RFI reduction or noise cancellation, well, we've had active noise canceling for audio since the 1930s that use phase reversal. Since the 1990s, we've had external analog RF cancelers like the ANC4 and the MFJ and others. But it's really only been in the past decade we've been able to do this digitally inside our receiver. So there's a bit of history. There's Henry Beveridge at RCA using spatial diversity. As you can tell, those were rather large pieces of equipment. That's Beveridge in the middle. And to get these multiple receivers to work together, he's the guy who invented ABC to sort of balance the signals coming out of each of the receivers. During the 1930s, and you can read the QST articles on this, but some folks at Holocrafters and others invented single control tuning for multiple receivers. And there's the DV1 from the 1930s. So what I'm talking about is really not new, but it's something that we need to get more use out of. The target back in the 1930s was multipath fading, because signals as they propagate take very short time differences in their bounces and paths. And that leads them to then mix together somewhat out of phase. And that's where multipath fading comes from. And diversity reception was the big method back in the early days of ham radio for fighting multipath fading. Became common throughout World War II and into the 1960s, using receivers like the AR-88 for triple diversity. And this was used in Canada for many years to get good quality signals from the BBC by shortwave, which were then rebroadcast in Canada. So diversity gain types and methods, though you can get diversity gain from space diversity with 2 antennas spaced apart. You can get it from different polarization, different angle of arrival. You can get diversity from 2 frequencies with the same signal. And there are various combining methods that give you various kinds of improvements. For example, my SDR Play RSP Duo has got built-in maximum ratio algorithm for getting sort of the best, about 6 dB of improvement in multipath fading. For array gain takes advantage of the fact that if you have two spaced antennas, the signal wavefront will hit each of them slightly at a slightly different time. And you can use delay lines or coaxial cables of different lengths to do the phasing, or you can add a variable time delay, a phase shift in your two-channel software-defined radio. And over on the right, you can see one thing you can get from a couple of antennas is signal-to-noise ratio gain, or you can get null steering. You can actually try to point the null from the two antennas phased together at the interference to reduce it. Analog versus digital beamforming. Back in the old days, you had to have all kinds of hardware delay lines hooked up to different receivers, and then you'd sum them in the receiver. The way to do it today is just simply have multiple receivers and then add the signals together once you get down to baseband. And if you have any questions about what I'm talking about, you don't understand baseband or anything like that, please ask. I'll be glad to explain it, but I'm trying to move along quickly. I'll drill down at any point if somebody wants to understand something I haven't explained properly.
Is this basically putting multipath to use?
Reducing multipath fading is one of the 3 value propositions of diversity reception.
Okay.
And the most common place you will see it used today is in cell phone towers and mobile communications, because there's a lot of multipath in the urban environment in VHF and UHF. And even in your home, in your modem, your Wi-Fi modem, some of you probably have Wi-Fi modems with 2 or 3 different antennas on the back. And that modem is actually taking advantage of diversity reception to try and get the best signal around the house. Okay, here's the primer. Diversity reception, there's 3 combining techniques: analog, which is external; digital, which is within the receiver; and human, which is my friend Mark down there in the lower right with his headphones on, trying to figure out which signal is stronger by listening to the 2 channels, one in each ear. Modern diversity receiver design, and I have 3 of them that I use. One is from Israel. It's called the Ephedri AFE 822. The RSP Duo is my second, and recently I got the Anand 7000, which is a lot more expensive, but it's a bit more heavy duty. What you have in your receiver is you have 2 channels with separate antennas, separate down converters, separate analog to digital converters, and you decode each channel separately, and then you mix the 2 signals together. You add them, and you add them and manipulate the phase and the amplitude so the signals add together constructively or destructively. And that's basically when you saw before that 40 dB reduction in my neighbor's halogen light noise. I was destroying the noise coming into my 2-channel receiver just by mixing the way I mixed them together. You can actually, it's all phase reversal, like 1 ± -1 = 0. So if you want to get rid of noise, if you can get a copy of the signal reversed in phase and add them together, then you can make it disappear. Array gain is very deterministic. As long as you have 2 antennas spaced a certain way apart, they each get an identical copy of the signal at a slightly different time. And by combining the 2 antennas together, you can create lobes, which is constructive, or nulls, which is destructive. And that will increase your average signal to noise ratio. So what I'm describing is like a 4-square array is an example of combining some antennas together to get lobes and nulls. Diversity gain is more probabilistic. It means you'll get the same signal arriving at different antennas at different times, and you'll get multiple copies of signal, and you really don't know how to get the best thing out of it. But with the right algorithm in your receiver, you can actually increase the probability of getting the best signal to noise ratio. And I'm talking about shortwave mainly, but you know, another example, you actually can do this with sound. You've been in meeting rooms where they have 2 or 3 microphones spread around the room, and those microphones can use diversity reception to get the best signal to noise ratio depending on who's speaking. They'll actually steer around the room. Now, noise cancellation is a little bit different because what you're trying to do is get a copy of the local noise and subtract it from the mixed signal plus noise to make the signal you want to hear sound a little bit better. So if you've got local noise mixing with the desired signal, this is what you can do. And you can do it analog with the MFJ and ANC boxes, or you can do it digitally with a software-defined radio that has 2 channels. On the left, you'll see the main antenna that you're listening to combining the signal you want to hear, which is in teal, and noise, which you don't want to hear, which is in black. And normally, if you just stuck your antenna on your receiver single channel, that's what you're going to have to listen to. But if you have a separate antenna that's optimized to pick up mostly noise and not so much desired signal, then you can bring that in, phase shift it 180 degrees and combine it. And at the output, you'll see a dramatic reduction in the noise that you don't want to hear, and no reduction in the signal you do want to hear. And that's what you saw in the video before. And that's how all these devices work, whether you do it analog or digital. So similar but different effects: diversity gain for multipath fading, array gain to get some lobes and nulls in directions you want them, and noise cancellation, which is where you figure out how to just pick up the noise and subtract it from what's coming in at your main antenna. Now, with only 2 channels, you have some limitations. Your diversity gain is limited to around 3 to 6 dB. Your array gain, the most you can get is single lobes or single nulls, but that can still be quite effective. For example, I use my diversity reception to do broadcast band DXing here in Western Canada, and I can go to a specific frequency, and by adjusting the phasing on my 2 antennas, I can hear different signals on the same frequency. So even with a single lobe, I can still shift it one direction or another and pick up different signals. And the noise cancellation is limited mainly to a single interference signature at a time. So you need to pick your worst offender and just do the best that you can. In my case, my worst offender is a house about 300 yards to the west of me with the poorly installed halogen lights and the switch mode power supply creating all kinds of noise that just radiates. And it drove me crazy for years. And now I don't even hear it anymore because I can just make it disappear. I did my demonstration already. Okay, so we're getting near the end here. You can get into diversity reception really cheaply. My ephedrine from Israel cost me $360, and I'm using US dollars here. It's 12 bits. It covers all of shortwave, and it works with Power SDR or LINRAD. That's in the top right-hand corner. My SDR Play, which I can't recommend highly enough to anybody who wants to get into this, for $280, you can go DC to daylight with diversity reception. It's just an amazing little box, and it actually works really well. And then the Anan 7000, which I finally broke down, I thought, okay, I'm retired now. If I don't spend my money, my wife will. No, did I really say that? I went and bought this in AN 7000. It's kind of a heavy duty diversity receiver, but it's wonderful. And that's what you saw me using before. My antennas on my lot, I've got a normal city lot, but I'm lucky to be next to a park. So you can see there's the aerial view of my house, and to my northwest, north and east, I've got a park. I've got my normal ham antenna just behind the house. I've got a 50-foot tower with a beam and a 40-meter dipole. But I've also put up 2 wideband loops 100 feet apart. And these are loops with an amplifier from a guy in Eastern Europe called LZ1AQ. And I can remote switch this array of loops either with 2 loops in end fire, 100 feet apart, or 2 loops broadside, 100 feet apart. And I can change my patterns, and I can do all sorts of stuff. I've also got some noise probes around the house if I just want to pick up the local noise and phase that. I've got some lousy antennas that don't pick up signals, but they pick up lots of noise. So that's my setup. And like I said before, with this two wideband loops in an array, I can actually create, and I've modeled it using NEC and using MMANA. I can actually create different patterns like you see in the lower left. When I listen to those stations on 730 kilohertz broadcast, I can switch these antennas to beam towards Vancouver to the west, or to beam towards Dauphin to the east, and hear the same frequency, 2 different stations. So that's what I play around with. My system performance is amazing for reducing RFI. It's not quite as amazing, but very useful with directional patterns. I don't really spend that much time focused on diversity reception because signals are so weak in Western Canada. I can't get the full benefit from diversity gain. So final thoughts, we focused on medium and HF today, medium wave and HF. All of these techniques actually work all the way from audio through to microwaves and even light. If you've ever heard of multiple input, multiple output, which is a big technique being used on the wireless front right now, that's basically another name for diversity perception. We've skipped all the math. There's lots of math if you like to play around with it, but I chose not to include it today. And if you want more information, there's all kinds of stuff on my website. And maybe before I close, I'll just bring up and show you that
Starting the economic development and improving people's lives as it faces
Sorry.
what Kim called a great life.
I'm just trying to switch now. I'm going to stop sharing my slides, and I'm going to share that video again so we can go back and enjoy the noise reduction.
Starting the economic development and improving people's lives as it faces what Kim called a great life and death struggle. Plenary meeting of the 8th Central Committee of the Workers' Party of Korea, which began on Monday. You can find more on this and all the stories we're covering at our website, voanews.com. We also have a mobile app that you can download via remote. I'm Marissa Milton, VOA News.
So another title for this presentation could be Make Shortwave Fun Again, because I know a lot of you probably have the same kind of RFI problems, and diversity reception is a great way to tame them if you want to put a bit of effort into that. So that's my presentation, and I'd be happy to answer any questions. And again, apologies for the computer failure before.
That's what we got big bucks in editing software for.
Yeah.
All right, are there any questions out there?
I have. Can you control the questions, Dan?
Can I control the who?
Do you want me to control the questions or are you gonna do it?
We got two people here, myself. Steve, in Tennessee, he's got his hand up.
Yeah, I have a question, and I don't know what category this falls into. When operating digital to a nearby very strong station, I noticed the throughput is considerably reduced because I'm assuming there is a time constant difference between a ground wave and the sky wave. Talking about 3 to maybe 4 or 5 megahertz. Got a tremendously strong signal on an orthogonal frequency division multiplex like Pactor-3 signal, but this throughput is dramatically slow, and I can liken it to the old rabbit ears TV, where part of the signal's coming in through the AC line and part of the signal's coming in through the tuner or through the antenna, and they're two different time constants, so you see a ghost. And I know the manufacturer of these modems that deal with this use digital signal processing as best they can to attempt to eradicate that, but it really doesn't. What you're doing seems, if I remember correctly, back in the old RTTY days, what you're talking about seems to have a solution for this. Am I wrong, or how would you describe, how would you get rid of that?
Okay, if your issue is that you're getting you're getting a multipath problem with,
Yes,
sorry, I got a phone ringing in the background. Do you guys get a lot of junk phone calls in the States?
No, we get
never,
we send
never.
them all to Canada.
We send them all to Canada.
Okay, so if you're describing a situation where you've got a ground wave copy and a sky wave copy of the same signal interfering with each other, the problem with that is the time difference between those two arrival times is going to be more than a phase shift can accomplish in your receiver. What you can use is a ray gain to find a null that you can place towards that local station and knock down the ground wave so that all you'd be left with is the sky wave. That's one potential solution.
Or could you do the other way around?
Yeah, you could try, but I think you'd have more luck knocking down the ground wave because it's more defined inside a null.
How would that be accomplished?
Well, with my two loop antennas spaced 100 feet apart, I can create steerable nulls and beams pretty much up to 10 to 15 megahertz. So I would just adjust the phasing between the two loops until I found that null in the particular direction that I need to find. That would be one way of doing it. But in terms of actually sorting out the time different, the arrival time difference is going to be more than you could accomplish by a plus or minus 180 degree phase shift of a signal at that frequency.
That's what that it's counterintuitive. Ham's looking for the strongest signal, and they go to the closest station to get that, when actually if they went higher toward the MUF, they have a better signal to noise ratio, and a lot of that goes away. It's very difficult to explain that, and I really don't have an explanation other than it works.
Yeah, no, I mean, it's very real. You always get a better signal as you go closer to the muff because there's less absorption. You can start out with that. Anyway, that's a separate topic, which actually I've got a series I just started on my blog trying to explain some of these things about propagation. So anyway, next, Daniel.
Yes, Daniel, take it away.
Yeah, if you could just give me the last characters of your website.
Oh,
Yeah,
how about I just put it, I'll put the URL in the chat.
That's
thank you,
great.
sir.
Okay, Victor.
Well, look back. Yeah, there we are. I wanted to go back to that last question of ground wave versus sky wave and negating the sky wave. Do you really want to do that, or do you risk losing another signal along that path that you do want to hear that's not a ground wave, so you won't hear it? But
Well, the point I was trying to make is if you had multipath fading with multiple copies of a skywave signal, you could use diversity reception to improve the signal to noise ratio. But if one of your signals is ground wave and one of your signals is sky wave, you can do the math, but you're probably going to have 100 milliseconds difference in arrival times. And that is more than you're able to phase shift to compensate for it, unless you are on a really low frequency. I hate doing math in my head. I used to be able to do math in my head, but when you get older, you need to reach for one of these.
Tell me about it. I've done that for years. That's been my lifesaver. Okay, Barry, what you got in chat?
We're good in chat right now. Victor, did they answer your question about MIMO and diversity?
There is a question from Don KE7ARH in chat.
I'm looking for it.
Okay, can you talk
Okay,
more
I got
about,
it.
yeah, can you talk
Go
more
ahead.
Can you talk more about the use of the SDR Play Duo for noise reduction? Is it possible to automate this seeking lowest noise automatically, or is operation required, and if so, why? That's a really, really good question. The answer is you need to do it manually. The algorithm in SDR Play RSP Duo does diversity gain, but it doesn't do noise reduction. There is no software out there that will do this for you automatically. I'll tell you how it could be done, but no one's actually done it yet. Do you want to know how it could be done? Okay.
Yes,
So,
that'd be great.
okay, almost all of the RFI that we get these days is power line related. And in some cases, it's power line noise, like from your power lines, but mostly it's power line related from a switch mode power supply, right? And a switch mode power supply will have 120 hertz harmonics, 120 hertz peaks when it creates wideband RFI. And another word for 120 hertz harmonics is 8.33 millisecond peaks that you'd see on the oscilloscope. And you could build an algorithm that could actually track these peaks and aim to decrease them, and that would drive your noise cancellation toward the sweet spot where you're phase reversing the signals. And I'll show you very quickly a video of how that works. Just let me pull it up here and share it, if I can still share. Yeah. Okay, here's that same audio video that I showed you before. But this time I've done something different. I've got a sound card oscilloscope rather than the audio coming out of it. So you'll be able to see either on the oscilloscope or a spectrum display, as I adjust the phasing, you'll be able to see the signal decline. Here we go. So there's no audio on this video, but there's the interference. I'm tuning the phasing. You can see it get knocked down. Now it's come back up again. That's your 8.3 millisecond spikes. Next, I'm going to switch to the spectrum scope. You can see the 120 hertz, 240, 360, 480, all those FFT spikes. Now, as I tune the noise down, look at the FFT reduces and those spikes go away. Okay, so that's how you could actually automate an algorithm to get rid of your interference from switch mode power supplies and power line noise No one's done it yet. I'm not I haven't patented this idea. I'd love for someone to do it.
Okay. Thank you. That's got a lot of good ideas there. Maybe somebody watching this will set it up and away we go. Okay, any more? I don't see any hands up. Any more questions? Anything we missed?
Everything's good in chat.
Good, good. That's what we like.
Yeah, sounds, here's another comment. Sounds like more like a GNU radio project. So I would have done this in GNU radio if I actually had a driver that I could connect a dual channel radio to GNU radio. I've done stuff with GNU radio on my YouTube channel. Unfortunately, I just don't have any way of getting those two channels coordinated into GNU radio, but that may be the way to do it. But I haven't figured out how to do it yet. Hey, I'm a retired guy. I'm not a really smart kid in university.
You're supposed to be age has wisdom, though, you know.
Wisdom I got.
Okay, are there any other more questions or comments? This is a really great presentation. Thank you, John.
Well, good. Thank you very much for inviting me. And if anyone has any follow-up or whatever, you can contact me through my website. Oh, I've got someone raising a hand.
Oh yeah, it's me, Dennis. John, I'm so thankful that you were able to come and join us tonight. I really appreciate you getting back to me when I invited you here, and I really appreciate your presentation. It's a lot of good information that I wish more manufacturers would pay attention to. One in particular, Flex.
Yeah, well, you know what's really funny, and I love Flex. I have a Flex. It's great gear. I love everything about Flex. The really funny thing is the software you use with the Anand radio. Guess what it's based on?
Power SDR.
Guess who wrote Power SDR?
Flex Radio.
Yeah. So
Yep. The old 5000 series actually goes back before the 5000. It goes back to what? The SDR 1000, I think. Is
yeah.
what
So you could do diversity reception back with the 5000 and 1000 by adding a second receive board in and using the same software. But I guess the guy that wrote it forgot about it, or no one's paying attention anymore.
Yeah, I actually have two 5000s here with the dual receivers.
Yeah.
Think about that.
Yeah. So you could do this right now yourself.
Yeah.
It's a lot of fun.
It's very cool.
But really, if anybody wants to just spend a limited amount of money and put up a couple of loop antennas like I've done and do the phasing and the noise reduction, I mean, my whole diversity setup, you would spend about $200 for the amplifiers for the wideband loops, and you can make the wideband loops out of anything. I use aluminum core PEX, but that's just my choice. And then another $280 for the RSP Duo, right? And so for around $500, there's your diversity reception system, and it'll work great. Okay, so I'll go away and leave you guys to it, and thank you very much for the invite.
Well, one more trip around. Any more got your hands up? No.
Thanks again, John.
Yeah, many
Really?
thanks, John. You really clarified something that you just don't come across too much, and you started a lot of thinking.
Well, good. And when you guys get through thinking and come up with solutions, please let me know.
I
Well,
have
my thinking is, why wasn't Flex doing what you're talking about?
Well, the answer to that is probably the military folks that really pay all their bills haven't wanted to do it.
Yeah, that's right.
But really, if you go to the source code for Power SDR, which is online in GitHub, and you look at the source code for that phasing window and how they do it, to add that into Smart SDR would take a 12-year-old 2 days. Okay, I'm exaggerating. You've got quality stuff, but it's really not hard.
It's not that difficult. Yeah, you're right.
One sledgehammer approach, if you really want to get a Flex or some other radio to do this, is you can use a common clock for the two radios. I think they both take 10 megahertz common clock in, and then you'll get your receivers in phase at least. And I think you can get the IQ signals off of the USB channel.
So here's the problem. Those receivers, the mid-range receivers already have the common clock. They have the coherent receivers. They have everything, except their firmware does not provide synchronized dual channel IQ data. I mean, if I could get synchronized dual channel IQ data like out of a Flex 6700, then you could write software externally quite easily to do all this stuff.
Yeah. I'm just being a sledgehammer here and saying you get two Flexes and run them with a common clock, and then just take one of the receiver outputs from each.
Okay, but there's still an issue with that, and that's latency in Windows and USB.
I buy
Right.
that.
Yeah, because you've got to get your IQ stream synchronized. Now, Flex uses Vita 49. So if they're providing those timestamps, you should be able to make it work. I'm sorry for getting deep in this, but like, yeah, okay.
Latency is a big problem with Flex right now.
Yeah, latency.
Big problem.
Latency is a problem for SDR in many respects. But you know, if people stick to Vita 49 or put proper timestamps in their data, then whatever problems with latency come out or occur in Windows, I mean, even Linux has got latency. You can fix it all just by rearranging the packets as long as you got timestamps. And you know, the folks figured out how to do this with stereo audio. It's the same problem, right?
Interesting.
It is. Okay, I'll stop now.
No, I love the conversation. This is good.
Happy to, and it's funny, I belong to another group. We meet Saturday mornings on Zoom. It's called Cycle 25. And they've got a bunch of people similar to you guys. Sort of this kind of Zoom meeting that's become popular over the last few years is a really good way to meet people and talk about common interests without all the politics of going to a local club meeting. Like we've met for an hour and no one's actually read the budget, you know, so.
We did have one quick advertisement there, but other than that, it's been pretty well free of the stuff we get in the ham club stuff. That's for sure. It's a different way of doing things. Not everybody agrees with video conferencing like this. Some of the old timers have a problem with it, but it does good for those who's using it.